Hello everyone. Today I'm going to talk about MISOFuzz, which is a modular infrastructure for scalable fuzzing orchestration. I am Nicole and I am a researcher at the Technology Innovation Institute in Abu Dhabi. I'm in the software security team and I work with Mike, which is our senior engineer, Norbert, lead researcher, Riti, fellow researcher, and Lucas, it's our unit director. Why did we build MISOFuzz? We wanted to generate a tool that was going to allow plug-and-play fuzzing. We wanted to make model checking and software verification easily usable for security researcher, as this and fuzzing requires a specific level of expertise to be run effectively. And then we wanted to simplify the integration of fuzzing tools to support cooperative fuzzing in a modular fashion. So to start, I'd like to introduce this example, which shows the motivation behind our tool. And the importance also of scalable fuzzing orchestration in software security. Fuzzing is a technique that is used to discover vulnerability in software system by sending various input to the system and monitoring its behavior. While traditional fuzzing approaches have been effective, they have some limitation. For example, they may not be able to generate diverse enough inputs to cover the entire input space, resulting in missing vulnerabilities. This is where cooperative fuzzing comes in. Cooperative fuzzing is a technique that combines multiple fuzzer and inputs to improve the overall efficiency and effectiveness of the fuzzing process, and can help increase the diversity and coverage of the input space, resulting in more vulnerabilities being detected quicker. And multiple factors can impact the performance of a fuzzing tool, including the complexity of the program under test, the size of the input space, the quality of the seed inputs, and of course the chosen fuzzing strategy. And balancing all these factors might be challenging, since different tools and techniques may be better suited to different use cases. And we can see this in our example. It's a snippet of C code with 2 bugs. And in order to reach these 2 bugs, we have to satisfy 2 constraints, which we call problem 1 and problem 2, which are in sequence. First sequence is problem 1 and then 2, and then the second one is vice versa. And we have 2 fuzzers. Fuzzer 1 is very good at solving constraint called problem 1, and fuzzer 2 is very good at solving constraint problem 2. So if we run only fuzzer 1, we will solve the first constraint. So we will cover line 2, as you can see from the table, and then 5 and 6. And if we run fuzzer 2, we will cover line 8, but not 9, at least not in an efficient way, and then 11 and 12. If we run both of them independently, then we will cover 2, 5, 6, 8, 11, and 12. But if we can do cooperating fuzzing, which means we're running them together and they're sharing their inputs, their seeds, then we can go through all the lines of the code, we can solve all the constraints and achieve the best coverage. So now I'm going to show you a practical example, and I'm going to run the same snippet of code on 2 AFL instances plus SimCC and on 2 AFL++ instances. So let's start with AFL, which is American Fuzzy Lob, a very popular fuzzer. This is the snippet of code that we're going to run. And plus SimCC. SimCC is a symbolic execution engine which will provide seeds, new seeds for the fuzzers. In particular, SimCC will analyze the source code, looking for branches and trying to satisfy their condition to increment the coverage. So now we're going to compile and instrument the source code, both with AFL, CLang, and SimCC compiler. Then we generate some random seeds to start. And then we can finally run the instances. And you will see that as soon as SimCC is started, the first unique crash is found. Yes, and you can see that now we have the first unique crashes. So let's go to the other examples now. Now we have 3 AFL++ fuzzers. 3 because in the previous example we had 2 instances plus another seed generator, so I think it might be fair to add another one here. AFL++ is an improved version of AFL, very, very popular. But you can see that this time the unique crash is not going to be found as fast. And actually, I've let this run for 20 minutes and the crash was not there yet. So what can we learn is that there is no unique solution for the fuzzing process. Some cases might require different tools. Let's go back to MISOFuzz now. Here you can see the high-level architecture design. One of the key features of our orchestrator is the scalability, of course. By allowing the user to choose how many workers instances to run, the orchestrator can be scaled up or down depending on the size of the fuzzing task and the available resources. This in order to ensure that the fuzzing process is efficient and also cost-effective. Another important feature of this orchestration is, of course, the flexibility. The user can customize the fuzzing process by choosing different seed generation strategies and by specifying various options for each fuzzer. This allowed for a more tailored and targeted approach to fuzzing, which can result in a more efficient and effective strategy indeed. Our fuzzing orchestrator consists of a main script that schedules fuzzing tasks to a set of worker instances. The user chooses how many of these and which fuzzer to run and for how long from the command line. And the job will be scheduled to the worker using RabbitMQ as a messages system, which allow for efficient communication between the different components of the orchestrator. Let's look now at the low-level design. The workers are isolated to virtual machine that are built on top of a Kubernetes cluster. The file sharing happens over NFS, and there is a distributed message queue for intra-cluster communication. As we've seen before, there are 3 main components of MISOFuzz: the scheduler, which schedules the fuzzing analysis job and aggregate the results; the message broker, that facilitates the data exchange between the scheduler and the workers, stores the fuzzing metrics and artifacts reports, and provide the event queue between the system; and then the workers. There can be either analysis, perform static analysis of source code, retrieve the task from the static analysis queues and push them to the result queue. And then fuzzing worker, different fuzzer, retrieve the jobs from the fuzz queue and push the result to the result queue. Why RabbitMQ? Using a message queue like RabbitMQ can offer several advantages for systems like fuzzing orchestrator. First and foremost, RabbitMQ provides a reliable way to pass messages between different components of the system. In a distributed system like our orchestrator, there might be different workers running on different machines, and they all need to be able to receive tasks from the main script. By using RabbitMQ as a message broker, we can ensure that tasks are reliably delivered to the workers, even if one or more of them are temporarily offline. In addition to reliability, RabbitMQ also provides a flexible and scalable way to distribute tasks, and it allows us to easily add or remove workers as needed and to balance the workload across them. And this can help to ensure that the testing process is indeed as efficient as possible and that all the resources are being used effectively. As we said, there is no one size fits all when it comes to fuzzers. Different fuzzers have different strengths and weaknesses, and they may be better suited to certain type of vulnerabilities or application. That's why our orchestrator supports several different fuzzers, including AFL, AFL++, SimCC, and FuzzBMC. So AFL, we saw it before, is American Fuzzy Lab, and it has been for here the state-of-the-art fuzzer. SimCC is the compiler wrapper which embeds symbolic execution into the program during the compilation and computes symbolic expression at runtime. AFL++ is the Google fork, it's the fork of Google's AFL, and is supposed to be better. It's usually faster, more efficient. And then FuzzBMC is a test generator for finding security vulnerability in C, and it incrementally injects labels to guide bounded model checking and evolutionary fuzzing engines to produce test cases for code coverage and bug finding. Another options that we have is how to generate the seeds. At the moment, we support two-way. One is using strings from binary. It's a practical method that is very common in vulnerability hunting. And basically, we extract the strings contained in the binaries and we use them as a starting seed. The pro is that it's very fast and does not need source code. We can do this also from binary only. And then the other side, we have ESBMC, which leverages bounded model checking and generates input that is relevant to the source code. So it takes longer than extracting the strings, but it's more precise. So in the current workflow, the user produces the fuzzing artifacts, the fuzzing job definition, and then the tasks and the result are exchanged with the workers through RabbitMQ. And the data is shared through a shared file system, can be NFS, can be SAF, whatever. And the data is exchanged between the workers and the user in this way. Here we can see a Grafana graph representing 32 instances of AFL of an AFL fuzzing campaign. And we see the initial startup and then of the program and then the actual fuzzing. And here we can see 32 instances of AFL plus SimCC fuzzing campaign. This is more interesting because we see the fuzzers, and then we see like the lower one, the light blue one, is actually SimCC, which is using less CPU. So now I'm going to show you a demo of MISOFuzz running. We have 3 workers, and we're going to run AFL plus SimCC. Again, we run it for 30 seconds. We have a configuration file with the path, and we are giving the source code, which is the same as before. We want 2 instances of AFL plus SimCC, 1 of SimCC. So you can see the 3 workers are accepting the job, and SimCC has started, and again, the unique crash has been found. We can actually see the same thing now from AFL++. So now we're running the same 60 second, and again is the same config file. actually 120 seconds, and you can see the 3 workers, 3 AFL++ instances running. And this can run for a while, but again, the fuzzers won't found the unique crash as while we speak. So this is to show how quicker it was to set up with MISOFuzz. It's just a command line interface for now, and you just need to set the timeout if you want, and the fuzzer combination that you want. You can either provide the pre-compiled, the pre-instrumented binary, or the source code, and everything is taken care of. Let's talk about further development, because there is a lot more than we could do. We want to implement a distributed fuzzing framework with ease of integration and modularity as priority goals, which means that we want to actually improve the performance of our fuzzing process and better distribute the workload across the different instances and share the discovered seeds. We want to develop a graphical or a web interface to make it even easier to control the result of the fuzzing campaign and to set up the different settings. We want to achieve telemetry-driven scheduling based on job performances and on-demand scaling depending on the available hardware resources and job backlog pressure. And we also want to compare our tool with the existing ones, a proper experimental evaluation. For now, we can do a theoretical evaluation. So MISOFuzz is implementing cooperative fuzzing, while MFuzz is implementing ensemble fuzzing, and ColabFuzz cooperating fuzzing too. So ensemble fuzzing is when you run multiple fuzzers but independently. So it's basically the third option that we saw in the examples in the beginning. MISOFuzz will implement a distributed scheduler leveraging FuzzBMC. In ANFuzz, the scheduler is as well distributed, while in ColabFuzz is centralized. The communication of MISOFuzz is over RabbitMQ, while MFuzz has a custom protocol and ColabFuzz use ZeroMQ, which has the pro of ZeroMQ is to be lightweight, but RabbitMQ allows for a more precise and wider communication, as in communication options. And then the fuzzers supported for MISOFuzz, for our AFL, AFL++, SimCC, FuzzBMC. Eventually, we're going to add FuzzX, which we are working on it, and it's going to be fully extendable through a simple interface. NFuzz support AFL, AFL Fuzz, FairFuzz, LibFuzzer, RADAMSA, and QSIM, while ColabFuzz is supporting AFL, AFL Fuzz, FairFuzz, QSIM, RADAMSA, onFuzz, libfuzzer, and is also extendable. And then MISOFuzz is leveraging bounded model checking to achieve a more effective coverage, while the other tools aren't. Here you can find the references of the thing that I've been talking about. And this was all for today. Thank you very much for listening. I hope you enjoyed the talk.